So this is lecture 9 in module 4. In this particular lecture, we will discuss how uh, the counters, especially the Johnson counter and ring counter. Okay, what's the working of basic ring counter and Johnson counter, and we'll also discuss how the shift register counters differ from basic shift register. So shift register means we know that it can store register means it can store data, and you can also use that particular register to for the movement of data. Okay, and by using this shift register, and if you use the output is fed back to the input side, this particular shift register will produce some sequence, a special sequence. Okay, this idea is actually used in shift register counters. Okay, the most commonly used shift register counters are a Johnson counter and a ring counter. The basic version is ring counter, and slightly modify you will get Johnson counter. Okay, we'll see what you mean by ring counter. Okay, here you can see a 4-bit ring counter state diagram. Okay, here you can see that if the initial state of the 4 registers are 1 0 0, next clock cycle it becomes 0 1 0 0. And again, if you apply another clock, again this 1 will be shifted to next position. Again, if you apply a clock signal, it will shift it to the next. And after this, again it will repeat the sequence. Again, it's 1 0 0 0 1 0 0, etc. So it will continue like this. Okay. If you take a 4-bit ring counter, you can see that there will be 4 different states. Okay, 4 states, and after that is again repeat. So this is state diagram. Now we'll see the truth table of that particular ring counter. For example, 4 output lines Q0, Q1, Q2, Q3, and assume that initially if you are using any flip flop, okay, see if you are using 4 flip flops, initial values of Q0, Q1, Q2, and Q3. Okay, it's 0, 0, 0, 0, 0. So first we need to make one value equal to 1. So Q0 is equal to 1. In order to get Q0 is equal to 1, we need to use the clear signal. Okay, okay, clear and preset signal. And first we will make all flip flop values are clear. Then one flip flop value to the preset state. So first we need to make this a sequence of operation that we need to perform. Before applying the clock signal, we need to apply the clear signal to all flip flops. So all output will be 0, 0, 0, 0. After that, we need to apply the preset signal to the first flip flop. Let be Q0. Okay. So we'll make this Q0 is equal to 1, and all other values are 0. This is the first state. Okay. So we need to apply clear signal, and we need to make the F of 0. That is first flip flop to the preset state. So the output of the first flip flop will be 1, and all other values will be 0, 0, 0. And after applying each clock signal, so you can see that this one will be moved to the next flip flop. So that's the shifting operation. So after first flip flop, you can see that this one is shifted to the next position, and again if you apply the clock signal, it's shifted to next and the last position. And again if you shift, it will move to the Q0. So in order to get like that, you need to connect the Q3 to the input of D0. Okay, we will see the waveform, circuit diagram also. And this pattern is actually known as a ring counter. Okay, so this is a single 1 is rotated. Similarly, if you want to rotate double 1, for example 1 1 0 0, if you want to rotate 1 1, you need to make 2 flip flops 1 initial. Okay, so different patterns are we can make by using this ring counter by properly applying the clear and preset signal. But usually the ring counter, one value will be 1 and all other values will be 0. This is a conventional way, and we can modify the circuit by simply applying 2 1s, and then 2 1s will be rotated. Okay, And now we can see the circuit diagram. Here you can see the shift register concept, serial in, serial out shift register concept. Okay, serial in, serial out shift register configuration. But you can see that the Q3 output of the last stage is connected to the D0. Okay, so this is an extra connection that we will use in this particular shift serial in, serial out shift register. And before that, here you can see the clock signal. So this is a negative edge triggered clock. It can be positive also, no problem, based on the available flip flop. Either you can use positive or negative edge. But before applying the clock signal, you need to apply the clear signal. Here you can see that the clear signal is active low. Okay, clear signal is active low, and active. Okay, and you can see that there is a preset signal also. Preset signal is active low again. Okay, but if you take the first flip flop FF0, you can see that in the first flip flop we are not connecting to the clear, we are only connecting to the preset value. So if you connect like this, and if there is a flip flop and there is a clear signal and a preset signal, okay, and this is an active low signal, means if you apply a 0 at the preset value, the output Q is equal to 1. Okay, instead of that, if you are applying a low signal to the clear signal, initially the Q output becomes 0. So here you can see that the clear signal or active low signal is applied flip flop 1, 2, 3, means output of flip flop 1 to 3 becomes 0, 0, 0 initially. Okay, but the first flip flop output, okay, it's connected to the preset signal. When the preset signal is active low, the Q0 output becomes 1. So you can see the 1, 0, 0. After that, the signal is disabled. Okay, we are connecting 1. After initial setup, we will connect these two values to 1. So clear and preset signals are disabled. Okay, only active during this low signal. Okay, this is a circuit diagram of a ring counter. Simply draw a single input, single out, sorry, serial in, serial out shift register and connect the output to the input side. And we need to extra add a clear signal. And flip flop 1, 2, 3 becomes connected to the clear, and the first signal, first flip flop is connected to the preset point. And we will apply a signal like this. Initially it is 1, and for a short duration we will apply 0, and we'll maintain it as 1. So we'll get a sequence like this: 1, 0, 0, 0. And after that, if you apply clock signal, it becomes 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Again, it will repeat. Okay, because the output of Q3 is connected to the input side. So now we can see the waveform also. So this is an active low signal from previous diagram. So here you can see the clear signal. Okay, initially it is 1, suddenly it becomes 0 before applying the clock signal. So initially all flip flop values are you can say that 0, 1, 1, 1. And we know that the first flip flop is connected to the preset. So after applying the low signal, the Q0 output is equal to 1 and all other values become 0, because you can see that f of 1, f of 2, f of 3 is connected to the clear signal, and f of 0 is connected to the preset. So based on that, the Q0 output becomes 1 and all other values will be 0. And after that, if you apply the negative edge triggered clock, that value will be shifted to each time. Okay, so this is the initial state. After that, you can see that this value becomes 0 and this one will be shifted. Okay, and after applying next clock signal, you can see that this becomes 0, this is also 0, this 1 and 0. And next clock cycle, it's 0, 0, 0, 1. After that, again it will repeat, is 1, 0, 0, 0. Okay, so this is a ring counter pattern. Q3 to Q0, if you observe, you can see that the ring counter pattern is repeating. Okay, so if you use a ring counter, we know that if you are using 4 flip flops, you will get 4 states. Okay, so the clock frequency also, if the applied clock frequency is f, the last output you can take f by, if it is 4 state, it becomes 4. Okay, divided by 4, and only 4 states. So if it is generally n states, it becomes f by n. Now we can see the Johnson count. In Johnson counter, you can see that the pattern is slightly different. Initially, it is 0, 0, 0, and after that, it becomes 1, 0, 0, 0, then 1, 1, 0, 0, then 1, 1, 1, 0, okay, then 1, 1, 1, 1. After that, it becomes 0, 1, 1, 1, 0, 0, 1, 1, again 0, 0, 0, 1. After this, again it go back to the first state. So if you are using a 4-bit flip-flop or 4-bit counter, you will get 8 different states. So 1, 2, 3, 4, 5, 6, 7, 8 states. So total 8 states. So if you are using n, you will get 2n states. So in the case of Johnson counter, that's the difference. If you take a ring counter, there's only n states in the case of ring counter, but in the case of Johnson counter, you will get 2 raised to n states. Okay. Now we'll see the truth table. If you compare with the ring counter, here you can see the last value is complemented and inserted. See, for example, if you observe the last state, it's 0, and this 0 is complemented and inserted to the first state. Okay, here it is 0. That 0 is complemented and inserted to the first state. Again, this 0 is complemented and inserted. So again, this 0 is 1. Now it is 1, so 1 is complemented and inserted to the first position. So this process will repeat. So you can see that the last output is complemented and fed back to the input side. Okay, that's a difference if you compare with a ring count. So this is the truth table. Initially, we'll make all the flip-flops in the clear state, that is 0, 0, 0. So this is the first state. And similarly, if you continue, you will get 8 states. Okay, after 8 states, again it will repeat from 0, 0 onwards. Okay. Now we can see the circuit used for Johnson counter, and here you can see that the last stage. Usually we will connect in the ring counter, Q3 is connected to the DC input. Now we can see that Q3 bar, because it's a complemented one. So we need to complement the output and we need to feed back to the input side. So instead of Q3, we will use Q3 bar. Okay, so Q3 bar will be fed back to the input side. So we'll get the output complemented and inserted in the input side. And another modification, you can see that here we are not using any preset signal. In the case of ring counter, to generate a sequence like 1, 0, 0, 0, this 1 should be forcefully we need to apply. So for that we are using a preset signal. But in the case of Johnson counter, there is no such circuit is required because there is no preset. All values are initially cleared and you can remove this particular signal. So sequence is like this. First apply clear signal to all flip-flops. After that remove that clear signal. So it is 1, we'll make it 0, then it will continue like this. But in the case of ring counter, this is not self-generated, self-started. Ring counter is not self-started, but Johnson counter, you can say that it's a self-started. Okay. Once you clear and if you switch on the supply, it will automatically generate the sequence. But for the case of ring counter, it's not self-starting. Okay, not self-starting. And another difference you can observe that the circuit modification. The output Q3 is connected to the input side, complemented and connected to the input side. So you will get sequence repeated. And if you are using n flip-flops, in the case of ring counter, you will get n states. Okay, n flip-flops, n state. But in the case of Johnson, if n flip-flops, you will get 2n states. Okay. And another difference, ring counter is not self-starting, but Johnson counter is a self-starting. And without using any additional circuit, see, usual way if you use a counter, other than this shift register counter, if you use any asynchronous or synchronous counter, if there is n flip-flop, there will be 2 raised to n states. Okay, and in order to reduce the state, you need to some additional circuitry is required. But without using any additional circuitry, in the case of ring counter and Johnson counter, you can reduce the number of states. Okay, that's the advantage of ring counter and Johnson counter. But in order to get a limited number of states, in the case of synchronous or asynchronous usual counter design, you need to use some additional circuitry, or the design process is very complex. But in the case of Johnson counter, it's very simple. So the frequency of the Johnson counter is f by 2n, okay, divided by 2n. The output f out frequency you can calculate by f by 2n. A ring counter, this is Johnson counter, and in the case of ring counter, it's f out is equal to f by n, because there are only n states. Okay. And this is circuit using D flip flop. Similarly, if you are using this is a waveform, okay, initially you can see that when you apply the clear signal, all values will be 0 0 0 0, and after applying the clock signal, the first value will be 1 and all other values will be 0. And again, after applying the next clock signal, it will be 1 1 and 0 0. After that is 1 1 1 0. Again, you can see that 1 1 1 1. Again, this last value is complemented, so 0 1 1 1. Again, 0 0 1 1. Again, it is complemented 0 0 0 1. Again, you will get a sequence called 0 0 0 0. Okay, so this is a waveform of Johnson counter, and this is exactly same Johnson counter by using a JK flip flop. In the case of D flip flop, only we need to connect Q3 to D input, but in the case of JK, you need to connect this Q3 bar to J. Okay, so Q3 bar is connected to J0 and Q3 is connected to K0. Okay, so this is Q3. That's only difference in when you use JK flip flop to generate the Johnson counter. But if you use D flip flop, only one input, so you can directly connect Q3 to the J input. Sorry, D input. Now it is a JK flip flop, so Q3 will be connected to J0 and Q3 will be connected to K0. Okay, it's all about Johnson counter and ring